Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, minimum total distance traveled. So basically this problem, we have robots and we have factories, and they are in a x-axis. So robots are represented here, and then you have factories. And so they are represented by their positions on an x-axis. And what is happening is that we get in the input each robot's position in the x-axis, and each factory's position is the first element here. Now each factory has also a capacity or a limit that we have here. Now what is this limit? Well, basically each robot is basically broken, and these factories repair the robots. And so this value here is how many robots a factory can repair. Okay. And basically robots can move either to the left or to the right on the x-axis. And then the goal of the problem is so that each robot has a choice of which factory to go to get repaired, except it has to have some capacity left, right? So if this robot goes to this factory and this robot goes to this factory, then it reached its capacity or its limit, and so this one cannot go to this one to get repaired. It has to go to this one. Okay, that's the idea here. Now the goal is to return the minimum total distance traveled by all robots so that they can be repaired. Now, what is the distance? Well, if this robot gets assigned to this factory, then the distance is just from 0 to 2. So the distance is 2. If this robot gets repaired here, the distance is 2 as well, 4 minus 2. If this one gets repaired here, it's at the same position, so the distance is 4, is 0. And so if we use that assignment, then this one took 2 to go here, this one took 2, this one took 0, so the answer is 4. And this is actually the minimum one, because if you get this one here and this one here, then now you have 6, so it's not, and if you will get this one here, now you have even larger cost. So the best way is 4, and so that's what we return. So that's basically the problem, is to find the minimum total distance that we can get by assigning the robots optimally to factories. Okay. Now, if you take a look here, the lengths are not too big, 100 for each. So this tells you that some oven squared should some time complexity of the length of robot by the length of factory should definitely pass. So let's take a look here. What's the best way to tackle this? So the first observation is that we are not guaranteed that this is in a sorted order. So it makes sense to sort both. Why? Because if you have a robot here, right, it always makes sense to assign it to the next, either the next one, the closest to it, right? So either this one, or if there was one before it, but it never makes sense to skip this one to go to the next one. That never makes sense, because that will only increase the distance, unless of course this one no longer has capacity. But it always makes sense to assign it to the closest one that has capacity, right? Similarly for this one, it makes sense to give it to the closest. So it's either this one or this one. We don't know which, but one of them. Here it's 6. We can do that. So it always makes sense to go to the closest one. And so it's in our interest to sort them. Okay, so we sort both factories. That's the first observation. So sort robot and factory array. That's the first thing. Now the next thing is, we actually don't know, because there is the variant of the capacity, so we don't know each time if it's better to go here or to go here. So that tells you we should try to do some dynamic programming recursive approach where we have multiple choices. And so what are the variables that we need to do? If we want to do a recursive maybe DP, we need to determine what is the state that we can use. Now, we definitely need to track which robot we are trying to assign and which factory we are at, right? Because each time, as we said, as we have the robots here, so you have a robot, I'm going to just make these the robots, and then you have a robot here, and then you have maybe the factory somewhere like this, okay? So each time when you assign a block of robots, let's say this one we assigned to this, and now its limit is 0, okay? We no longer need to examine this one. Once it reaches its capacity, we should always start trying from this one. Let's say we assign these two to this one. We should no longer look at these. We should only look at this one. Okay? But what do we need to maintain? Well, we need to know which position we should start considering, because if we already reached the limit for this one, when we are trying to assign this robot, it doesn't make sense to look at this one. So each time we need to have the index of the robot we are at and the index of the factory. So our state needs to have the index of the factory. So index of factory we are at in factory array. And R is similarly the index of the robot in robot array, okay? Now the other thing that makes sense to look at is, well, let's say this one has limit of 2 and we assign this robot to it, okay? Now it has a limit of 1. So we can still assign this one to this one. We can still try. We will try this one and this one, but let's say we try this one. Now this one, so we need to know if we can. So here we can, so now the capacity is 0. For this one we can't, so we have to go to the next one. So we need to keep track of how many robots were already assigned to the current factory, so that we can know if we can assign the current robot to it or not, and the next robot to it or not, okay? So we also need, let's call it K, which can be the number of robots already assigned to factory F, right? Now, the other thing, so you need the parameters for the function, but you also need what the function returns even. So our function, let's call it cost, because we are trying to minimize the total cost. That's what we are trying to minimize. So that needs to be our function value. So the parameters we said are this, is basically the minimum cost to assign robots up to R to factories up to F, right? That's basically what this is. With factory F having K robots assigned. That's essentially what the state is going to be. Okay, so now we need to examine for each robot what are the choices. That's what we need with dynamic programming here. So we have 2 choices for robot R at each point in time. So when we are here, well, if the current robot still has capacity, we can either assign it to it, or we can skip it and go to the next one. Okay? And so here, we can either robot R skips factory F, or robot R assigned to factory F. Now this is only possible only if there is still capacity, only if factory F still has capacity. Well, what that means basically is if K plus 1, which is the if we assign this one, the total is K plus 1, this needs to be under the limit, or equal, less than or equal to the limit of the factory. And to get the limit, which is just the second position in the array here. That's the limit, okay? And those are basically the 2 choices. Now, one thing I want to mention here is that, let's say maybe if we had just 2 robots, but a lot of factories. Maybe at every position here. Okay. So for this one, it makes sense to skip this one, and then try this one and try this one. So with this solution here, what will happen is that because we have this recursive choice of skipping, this state of assigned to this is basically two calls to skip, two recursive calls to skip, and then a call to assign. And then we'll try another call to assign, three skips and then assign here. All those choices will be examined because each time we go through a skip choice and then assignment choice, right? And so we will evaluate all of them. We'll even evaluate skipping all four and going here, if that's the best choice, right? And so this is really, we'll examine all the choices regardless of where the positions are. Now, another thing we need to examine for a DP like this is the base cases. Well, the first base case is simple, is if we are at the last robot, then we are done. So if we already assigned the last robot, we are done. In that case, we just return 0, and this will get added to the cost. Now, if we reached the last factory, but we haven't reached the last robot, that means, well, we didn't assign all robots, so that's not a valid solution. So to exclude this case, we just need to return infinity so that it's not the minimum, so that the minimum is something else, where all robots get assigned. Okay. Now, one thing I didn't mention here, these are the choices, but what's the cost for each choice? Well, for this one, we didn't do any assignments, so no cost. Now, with this one, we did do an assignment, so the cost that we need to add is the distance, basically. So here we are assigning robot R to factory F. So the cost is just the distance between the robot position and the factory position. And that's basically absolute value because we don't know, like we may be in this case where the robot is assigned to the previous one or the robot is assigned to next one. We only need the distance between them. And so we need to do the robot position, which is robot R, minus the factory position, which is just the first position for the factory here. So it's going to be factory F at position 0. This is the cost that we need to add. That's pretty much it. With this, we should, for the two choices, we just take the minimum, right, and return it. So in the overview, so we said we need a function like this with these are the parameters that we need to return. We said we also need to sort both the factory and the robot, so we sort those. And then we need to return the cost. We start at the first case, so we are the first robot at the first factory and no robot was assigned yet. So that's the first one. Now let's just do our base cases, which we said here. So like this. So this is going to be if this is equal, then we return 0. And then if we reached the last factory, but we haven't reached the last robot, then we want to return if. Okay, so if we reach the last factory and we haven't assigned a robot, that's not a valid state. So we need to return infinity so that it's never the minimum. Now we need to do the two choices that we have here, which we said, so we just need to turn this into code. So the robot skips or the robot gets assigned. That's one of these two. So this is only if this is a valid solution. So we need to go to the next state, same thing here. Next state is basically, for this one, because we skipped the current factory, we need to go to f+1. And then we stay in the current robot because this current robot has not been assigned yet. Now for the next factory, we haven't assigned any robots, so the value here needs to be 0. Now let's call this skip choice. And this is the assigned choice, right? Now the cost for the assigned choice, we stay in the current factory because maybe it still has capacity. We go to the next robot because we already assigned the current robot to factory F, and we increment the number of robots assigned to the current factory, right? Because we just assigned robot R. Now, once we do this, we just need to return, for this case where we have two choices, we need to return the minimum of the two, of the skip and assign. And then here, it means we didn't have any assign choice here, so we just return the skip choice. And that's pretty much it. Now, we need to memorize this. You could use a memo hash map, but I will go with the simple route with in Python with LRU cache with a max size, without a max size. And then we can run this. Now this needs to be a check for equal, same thing here. And then we need this, of course. And looks good, so let's submit. And this gets accepted. In terms of time complexity here, time complexity is going to be basically the space for f multiplied by the space for r multiplied by the space for k. And those are, if we have like, maybe r is the length of robot, f is the length of factory, and maybe k here is the max capacity for a factory. Now in that case, our time complexity is just going to be the multiplication for all three, because that's the number of states we have here. This is both in terms of time complexity, but also space, because we cache the result. So both in time and space, this is going to be our complexity. Yeah, and that's pretty much it for this problem. Thanks for watching, and see you on the next one.